talk to you. I'm Peter Mell. I'm from NIST. I feel a little of an oddball here because I'm a computer scientist. And not only am I a computer scientist, but I got redeployed 6 months ago to doing academic research. So my world has changed dramatically. And last November when I did my performance review and my boss said, "You're doing a great job, I'm doing all your work with somebody else." He told me to look at big data technology. And you can't exactly research something unless you know something about it. So I will plainly admit, as of last November, I knew nothing about big data technology. I didn't know how to define it, didn't know what it meant, didn't know what it was used for. Do you guys? Is anybody here? I see some hands waving. So we're going to dive into it. But before we start, I want you to know that I'm going to give you my opinion. This is a real disclaimer. I am not representing NIST. Okay, so be very clear about that. And you'll see why, because I'm a little opinionated. I disagree with some industry experts. And management I haven't convinced them yet that I'm right. So take it for what it is. We are going to start off with a sort of introduction. I'm going to give you my definition of big data. This is sort of a funny thing to do, because years ago I started the NIST Cloud definition. So I feel like I'm reinventing things here. We're going to talk about taxonomies, security implications. We'll go into some major MapReduce, we'll go into some major big data implementations, particularly MapReduce, Hadoop, Bigtable, Amazon's Dynamo, Cassandra. But I don't want to just bury you with technology, although that would be fun. We could spend hours here. What I want to do is I want to convince you that big data is a meaningful term, that it's not just marketing hype, and that it means something very specific, and that it's here for a very specific reason. And I want you to understand the computer science underpinnings under that term, which is going to help you understand why might I use big data, when might I use it, what type might I use it, and if I do take that plunge to use it, what am I losing? Because there are no silver bullets, no holy grails. When you adopt something new to achieve a purpose, you give up something that you used to have, and that is very, very, very true in the big data world. So, big data is mainstream. I get The Economist, mainstream magazine talking about big data. We create lots of data, that's clear, but big data doesn't just mean a lot of data. A little bit confusing, we'll get to that in a minute. But we certainly are creating a lot of data. When bin Laden died, for example, we had 5,000 tweets per second going on for a while. Of course, when Beyonce got pregnant, 9,000 tweets per second. So you can see the big data we're creating isn't always important data, but it is data.
Well, it's a song.
For sure.
Beyonce.
Now, so do I have it here? So, in 2010, we're producing 1,200 exabytes. What is that? What's an exabyte anyway? Back in 1991, we had to invent some new terms for sizes, the zettabyte and the yottabyte. The yottabyte we don't even use yet, but a zettabyte is about how much information we're forecasted to be producing right now. When you move up these terms, you multiply by 1,000. It's fairly common to buy a terabyte drive now, but to actually fill that terabyte drive with meaningful data is a whole other story. So we've got all this data, and we can't store the data that we've created. You just look at the amount of storage we're actually creating. It's much less than the amount of information we're creating. And Tim O'Reilly, who is the guy that started the famous series of software programming books with all the animals on the covers. If you're not a programmer, you won't know what I'm talking about. But he says that we've started an industrial revolution of data. certainly there's some marketing there, certainly there's some hype here, but there's some truth, and let's explore what that change really is and why it's happening. So I mentioned we can't store all the data we produce, and we have a lot of data. About 95% of the data that we're creating is unstructured, meaning we have structured data. That's where, think a relational database, we have a schema, we've got well-defined tables and joins between the tables. You have semi-structured data, which is sort of self-defining. An example of that is an XML document. The XML document should have a schema, or it's bounded by valid XML tags. So you know what tags to expect, you just don't know what tag's coming next. It's semi-structured, it's self-defining sort of a structure. And then you have unstructured data, which is English prose, you have no idea what I'm going to say next. So it's unstructured. And we'll get to this in a minute, but the relational database systems that we have today do not handle the unstructured data particularly well. You can force whatever data you want in any database you want to. It's just, can you do it efficiently? Will it run quickly? Can you query it in a powerful way? And the key observation here is that relational database management systems are being challenged to handle the amount of data, how fast that data is coming at us, and the variety and structure of that data. Really?
Can you explain that chart? The
Yes.
top line is information, the gap between the lines is information that is created but not stored?
Correct. Yeah, so it's more primitive than that. It's just how much information have we created, how much storage do we produce.
Right.
Not that we
So where does that data live?
What?
Where does this alleged unstored data live?
It's deleted.
It just lives on the wire?
What? It just disappears.
It comes in and dribbles out on the floor, never gets stored in.
Yeah.
Doesn't need it.
Never, yeah, never been a bit about it. Yeah.
Okay, so let's look at industry. Industries define big data, and O'Reilly says big data is where the size of the data becomes part of the problem. That's decent but vague. EMC, IDC has another definition that focuses on what has become termed as the 3 V's: the volume, variety, and velocity. And we talked about those in the last slide. IBM agrees with them: volume, variety, velocity. Microsoft agrees with them. But I disagree a little bit, and that is that industry seems to be pointing out, they're saying volume, variety, velocity, that's a big data problem. But what I ask is, what setting of those attributes creates a big data problem? Attributes themselves don't create a big data problem. What setting of those attributes and why? And so here's my definition. And so I use the 3 V's. I really don't like the variety thing, so I just say data representation. But notice I've got the 3 V's on the top. And then I've got 2 conditions. I say that some setting of those attributes, number 1, it's a big data problem if it limits the ability to perform effective analysis using traditional relational approaches. So if you can't use a traditional relational database and analyze your data that has some sort of assignment of those values, if your relational database is failing you in that sense, then you've got a big data problem. And notice that doesn't mean that you have a lot of data. You can have a very small amount of data and still have a big data problem according to this definition. And I realize the cognitive disconnect there. The reason it exists, it's not my fault. It's industry. Okay, so all you industry people understand, you guys are the ones that said that variety was part of the term big data. And I'm not going to disagree with you, but I'm just going to point out to you that if you guys say variety is part of the problem, that means we can have an itty-bitty little bit of data and it can be a big data problem. And let's explore that. And let's explore why. And I believe that industry isn't wrong, and I believe they're right in doing so, And they're right because even a very itty-bitty little bit of data, if it's structured in a certain way, you may not be able to query it effectively using traditional relational approaches. To prove that, there are certain graph problems that you could represent in a graph database. And by the way, you can push the graph database into a relational database if you want to, but it won't be efficient. But there are certain graph problems where SQL will not give you the ability to do certain queries that you might want to do, or certainly not do them efficiently, whereas a graph querying language will. So we're not talking about a lot of data here, we're talking about the representation of the data and the ability to query it. So that's that first clause, a limit in the ability to do analysis using traditional relational approaches. The second is some assignment of those attributes with your data ends up requiring the use of significant horizontal scaling for efficient processing. So vertical scaling, I buy a bigger, better computer, right? Horizontal scaling is you have many, many computers working together, or more and more computers working together. And in the cloud world of today, that usually means commodity, cheap computers, but not necessarily. And if you take a relational database and you start clustering it, and you're using normal configurations, and we're not doing extreme, strange things, the clustering will work to an extent. You add a new computer, your overall performance increases. At a certain point, I think it's around 8 or 9 or 10 servers, when you add another server, your performance actually decreases. Under normal problems, normal kind of configuration. Why? The reason is because the database cluster requires inter-host communication to keep all the data current. If you remember your database class from long ago, which by the way, I never took the database class, so think about who you're actually getting this advice from. So your database guarantees you consistency. It guarantees you that when you write the data that actually gets written, that it doesn't interfere with anybody else's data, that it doesn't change over time, and eventually when you read it again, you're going to get the right answer. Your database guarantees you that, and that requires a lot of communication among the database cluster, which means that as you add computers to that cluster, eventually your performance is going to go down, not up. Now, notice here, the second clause said nothing about relational databases. And that's because for a certain class of problems, you can actually solve a big data problem using a traditional relational database. To sort of steal the thunder for that, if your problem is embarrassingly parallel, then your traditional relational database may actually work for this. And you may actually be able to scale it horizontally, almost linearly. However, most problems do not fit that mold. So unfortunately, it won't work usually. So usually, adopting big data means getting away from relational databases. So let's take a step way back, before I was born. Okay? And I'm starting to get old, actually. I have gray hairs. So, 1970, Edward Codd, IBM, invented the idea of a relational database. Several years later, SQL was developed. We had a powerful querying language with this new concept of tables joined together. Prior to 1970, when we didn't have relational databases, we did store data. We had databases of a sort. And oddly enough, the big data solutions the vendors are giving you today many times look a lot like the solutions of the 60s. So just like in cloud, some people said, oh, there's nothing new here. If we're just going back to sort of a mainframe model, In big data, some people could say, oh, there's really nothing new here. We're just going back to 1960s technology. But just like cloud, with cloud there really was some meaningful technology here, some real transformation. I believe with big data we have some real transformation here. Basically, we have taken relational databases and we've used them and loved them, and we're going to continue to use them and love them. But we've done as much as we can with them, and we still have more data that won't fit into them. And so we're taking the next logical step. And that next logical step is to say, okay, what can I do with the rest of the data out there? And that means going back to technologies from the 60s that actually are much more scalable than the relational databases that we have today. So I'm still